The key with implicit differentiation is just understanding how to differentiate the y's. Because we know how to differentiate the x's, none of that has changed, but we differentiate the y's a little bit differently because we're doing it with respect to x, not with respect to y. So if we just for an example, if we start off with just saying that y equals x squared plus 1, so we'll just start with that. And then we say, let's say that we wanted to differentiate y squared, which would be x squared plus 1 squared. All right, if I wanted to differentiate this, then, so I wanted to differentiate y squared. I want to find what its derivative is. Let's see what the right side becomes using the chain rule. So the outside, the big idea is something's being squared. So we know that we're going to take the derivative here of 2 to that something, x squared plus 1, and then to the first power. So that's the outside's derivative. But now we need to multiply by 2x, which is the inside's function's derivative. All right, I want you to notice here what happened. We have a 2 out front, and then do you see that this guy right here is the same as the original y? So we have 2y, and then do you notice that this guy right here would be the original y's derivative, y prime. So in other words, bringing this side down, y squared is going to equal, when we take its derivative, is going to equal the derivative we think. I mean, if you think about what the derivative of something squared is, it's 2 times itself, or 2 times y, bring that down, our shortcut rule, and subtract 1 from the exponent. So it's 2y, but then, because of the chain rule, and because we're actually differentiating with respect to x, not respect to y, we have to tack on a y prime. So the shortcut here, hopefully that made sense, but the shortcut here, or implicit differentiation in a nutshell, is differentiate everything, but every time you differentiate a y, tack on a y prime. And then in the long run, we're just going to solve the equation for y prime. All right, so let's take a look at our first example, and I want to do this in two different ways. First, I want to do this solving for y and differentiating the way that we have been differentiating. So if we solve this equation for y, we would get y equals, and it would be the square root of 25 minus x squared. And I'm hoping you guys recognize that equation, that is an equation for a circle with a radius of 5 and it's centered at the origin. So when we differentiate here, we actually end up with the semicircle for that. So let's take a look at what y prime would be using our chain rule. So the big idea here, if we do our chain rule, we have u equals 25 minus x squared, and the big idea is the square root of u. So looking at this, we know that the outside's derivative is 1 over 2 square roots of u. We know the inside's derivative is negative 2x. So if I multiply those two things together, and I go ahead and reduce, I'm going to end up with negative 2x over 2 square roots. Instead of u, we're going to put back in the 25 minus x squared. Now looking at this, we can see that it will reduce, the 2's will reduce. So we have this will be equal to negative x over square root of 25 minus x squared. All right, so our derivative is negative x over the square root of 25 minus x squared. And so that's the way we've been doing this. Now let's go ahead and take a look at how we would do this with implicit differentiation. Remember, as I said, with implicit differentiation, we're going to differentiate everything. We're not going to solve for y or anything. We're just going to differentiate as is, and then we're going to tack on a y prime because of the chain rule anytime we differentiate our y's. So if our original function is x squared plus y squared equals 25, then we're going to simply we're not going to solve for y, we're just going to differentiate. So our first derivative would be 2x. Our second derivative would be 2y. But we just did the derivative of y, and since it's with respect to x, we're going to go ahead and tack on a y prime. And the derivative of 25 is 0. So now if I solve this for y prime, because that's what we're trying to find is that derivative, I would get negative 2x. And then when I divide by 2y, the 2's will cancel, leaving me negative x over y. And now maybe you're saying to yourself, well, that is not the same thing as what we got in the previous example. However, remember what we said y was equal to. So if I come down here and I replace the y with what it's equal to, which is the square root of 25 minus x squared, you see that this is indeed the same as this. So again, it's just a different way to differentiate. And for this problem, was it necessary? Absolutely not. But we're going to go on to a couple more examples where it will be necessary because there's no other way. You cannot solve for y in some problems, so then we need this process in order to help us in those cases. All right, so moving on to this next example. On this one, we cannot solve for y. We're not going to be able to solve for y. So we will actually have y's in our answer, and that's okay. In the last one, we could substitute the y, but in this problem, we're not going to have a y to substitute in because we don't know what that equals. So this one we have to use implicit differentiation on, and we are going to have y's in our final answer, and that's okay. So again, we are just going to go ahead and look at this problem. We're going to do the derivative of x cubed, do the derivative of y cubed. However, we're going to tack on a y prime. And now when I go to this next side, I have to realize that this would actually be the product rule. Because 6x times y, that's two different functions being multiplied together. So I need to apply the product rule. So if you remember, the product rule is f prime g plus g prime f. I'm going to look at f being 6x, and I'm going to look at g being y. So f prime would just be 6 times y. And then, because that would be 6 times my derivative of f times my g. Then I'm going to take a look at what is g prime. Well, g prime, the derivative of y would be 1. But because I differentiate a y, it's going to be 1 y prime. So the derivative of y is y prime, and then I'm going to take that times f, which was 6x. All right, now my goal is going to be to get the y primes on one side by themselves and just solve for y prime. So I'm going to keep this one y prime that I have on the left already, but I'm going to subtract this y prime from both sides, so 6x y prime. And then I'm going to keep this 6y, but I'm going to subtract this 3x squared from both sides. Move it over to the other side. All right, and then I notice that I can take a y prime out of both of these here. So if I take out the y prime, I'm left with 3y squared. Sorry, make sure that's a y prime. 3y squared minus 6x equals 6y minus 3x squared. And so my final step from my final answer here is to go ahead and divide both sides by 3y squared minus 6x. So I have 6y minus 3x squared over 3y squared minus 6x. And that is my final derivative. And again, there are y's, but that's okay, because what do we use the derivative for? We use the derivative to find instantaneous rate of change at a particular point. So we're going to be able to replace the x and y with the x and y values of the point. All right, I just wanted to work another example here with you for this. And again, this seems like it's a fairly simple process, but like if you notice in this next example, we have a chain rule and we have a product rule. So sometimes we have to do those other different rules that we have within implicit differentiation. So taking a look at this, if I'm going to differentiate the left side, I see that I have a function inside of a function. So I'm going to have to use the chain rule. And I don't know how comfortable you guys are yet, so I'll go ahead and go off to the side and do the chain rule if you're not comfortable doing it without doing our little shortcut here, our little chart. So I'm going to say that u equals x plus y, and I'm going to say that the outside function is sine u. So we know that the derivative here is cosine u, so it'll be cosine of x plus y. All right, and then for our derivative here, we know that it's going to be 1 plus 1 y prime. Don't forget to tack on the y prime. So our left side for this function is going to be cosine x plus y times 1 plus y prime. And then our right side is going to be the product rule. And I'm going to look at this as my f, and then this is my g. So if I do f prime, it would be 2y, but again, I have to do y prime, times my g, and then plus g prime, which happens to be a negative sign in this case, times my f, y squared. All right, now the hard part's done. So it's just a matter of doing distributive property and getting the y primes by themselves. So over here on the left-hand side, I'm going to go ahead and distribute the 1 plus y prime to the the cosine x plus y to the 1 plus y prime. So I'm going to have cosine x plus y, and then plus y prime cosine x plus y. And on the right side, I'm going to have the 2y, y prime cosine x minus y squared sine x. I just kind of changed the order on a couple things there. All right, so again, our goal, get all the y primes on one side, all the non-y primes on the other side. So I'm going to keep the y primes on the left. So I have y prime cosine x plus y minus 2y, y prime cosine x, because again, I'm moving this over. And then on the right, I'm going to have that negative y squared sine x that was originally there, but then I'm going to subtract off the cosine x plus y. All right, and for my final step, well, we'll go ahead and factor out the y prime. Sometimes I know I get ahead here and skip some steps, so I'm not going to do that. Okay, so if we factor out the y prime, that would be what our left side looks like, and our right side has stayed the same. All right, so our final step is to divide by this thing right here to get y prime all by itself. So our y prime is going to equal y squared sine x minus cosine of the quantity x plus y all over cosine the quantity x plus y minus 2y cosine x. And we're done.